Hi everyone, welcome to Advanced Surveying course. The first module is about error analysis and positional quality. By the end of this lecture, basically we're going to provide you an overview of what you've learned in other courses about error analysis, which is going to be including theory and practice, like terminology. We're going to talk about precision estimation, error propagation, both random and systematic errors, and we're going to talk about a little bit about the least square adjustment. I know you know from Comps B, but we're going to extend it a little bit more. And then hopefully by the end of this lecture you're going to have a good understanding of the nature of uncertainty in surveying measurement, which is coordinates, heights, slope distances, and angles, obviously vertical and horizontal angles. So I put this code because I found it interesting. Let's have a look together. So although this may seem a paradox, all exact science is dominated by the idea of approximation. So there is no exact thing in the world. When someone telling you that he or she knows the exact truth about anything, then you should be safe, because he or she is not an exact man, because there is no exact truth, and there is no one in the world who knows exact truth about anything. So every careful measurement in science is always given with the probable error. So there is always an error in anything. So every observer admits that he is likely wrong and knows about how much wrong he is likely to be. So in this course, we probably want to teach you, no matter how hard you're trying to not having any error in your measurement, you're still going to have some errors still, and you should be able to identify the nature of those errors in your measurement and make sure that you can minimize them, or at least to make sure that you can achieve the certain accuracy or required accuracy for your job. So I think that was a good start. Let's have a look at some of the terming that you've obviously heard from other courses. I remember I've talked about quality assurance in automated surveying system myself. I'm pretty sure you must have heard quality control, and then I'm going to define quality assessment, which is what we are doing in this course and this particular module. So quality assurance is a process or system oriented and focuses on prevention. So by doing quality assurance, we want to make sure that we prevent an error. So that's why you have a list of things that you tick, and you make sure that, yeah, I've collected this, I consider that, I put the index error correctly. So you make sure that you do or follow the steps for that particular job. What is quality control though? Is the product or results oriented, focuses on identification of errors, defects, or uncertainties that will impact the final results. So quality assurance is prevention, quality control is about identification. But what we want to do in this course is mainly quality assessment, which I would say this is going to be the method or process for identifying the magnitudes and nature of the uncertainty that will affect the quality assurance and quality control. So it's very important for us to know how we can do the quality assessment for our job and make sure that we are achieving the certain accuracy. But before I go further, I want to talk about measurement uncertainty. We all know what's error, but is it correct term to use? I'm not quite sure. Why I'm not sure? The term error implies that a true value is known. So if we say we have an error, we should have the true value. But do we really know the true value for our measurement? My answer is no. So what we call it here in our course and many other courses, we call it sigma, or a standard deviation. which is basically for a large population, as I said, which is shouldn't be the right term. We should say S or capital S. So I would say we have sigma, we have S, we have U. As I said, this is the standard deviation of the large population. So large population. Good. We have S, which is the standard deviation of the sample. Good. And then we have uncertainty. But what is uncertainty? The uncertainty, or U, as described here, are sometimes used interchangeably with sigma. So you might see in this course, I might say uncertainty, but I really mean standard deviation. So it can be used interchangeably. But you should be able to assess the correct meaning from the context of the question or the statement. So many manufacturer precision specification, they will say sigma, but what they actually should mean is S, which is the standard deviation of the sample. But because the test they're doing is over the smaller population, they're not going to do the test for million measurement, which is a large population. They're going to measure it a few times and under the certain condition and make sure that what's the sigma in the way that they say, or to me is correctly should be S. So if I want to define uncertainty, I would say means doubt. It's very important about the validity of measurement or results of measurement. What is our measurement? Surveying is coordinates. It is distance, can be slope or horizontal, can be a horizontal or vertical angle, and can be height. So any of those can be our measurement. So it is an indication of how wrong a value may be from what is basically should be, and is used to quantify the level of survey quality. So if I have the less uncertainty, it means that I have better quality for my survey. So uncertainty is expressed as a standard deviation, as I said. You might see in the manufacturer, they will say sigma for angle, sigma for, I don't know, distance measurement, or sigma for, of course, for sigma for distance measurement, they usually say, for example, 2 millimeter plus minus, I don't know, 2 ppm, because it's the ADM thing. But it might be sigma for height measurement, I don't know, all sorts of things. When you see that, just make sure the sigma they are telling is in 68% confidence level. But sometimes you need 95 confidence level. That I'm going to talk about how you can convert it. It's very easy. You simply multiply the sigma by 1.96 or 2 roughly, and then you can get the 95% confidence interval. But as I said, in this course or many other courses during this program, the whole program, you might see these terms are using interchangeably. So you just need to understand the concepts of them, but the terming is not really matter. So the next slide, I want to talk about 3 usual terms of uncertainty that we are using in surveying specifically. I'm pretty sure you've heard positional uncertainties, and I'm hoping that most of you know what does it mean, but just let's have a look and try to repeat. So what is positional uncertainty? It's basically these terms is adopted from the documents from the body that basically sets the most used surveying standards, which is called Intergovernmental Committee on Surveying and Mapping, or you might have heard the name ICSM. So Intergovernmental Committee on Surveying and Mapping. So I'm going to search this term, or I also provide, some of the documents on the study desk. I really recommend that you go and read some of those specifications, especially the one I'm going to provide you in the second module is going to be guideline for conventional traverse. And I also recommend you go and have a look guideline for adjustment and evaluation of survey control. I found it very useful and is very helping the student to grow their learning about the standard and requirements in surveying specifically. And this is the guideline is using in New Zealand, so it's not only Australia, it's using, as far as I know, some of other countries also, they look at this document because it's very well written and they will use some of the terming. So, back to where we are. Here, positional uncertainty, or PU, is known as a survey, can source the PU for or uncertainty relative to the datum. But what this datum means here is the control network that is constrained by national datum stations. In our case, it's going to be GDA, which can have their location defined by positional uncertainty. So, I would say positional uncertainty is probably mostly for PSMs that you have and is relative to the national datum in our case. Talking about GDA, I just want to make sure that you all know that there is a new GDA coming, which is GDA 2020. It's going to come to effect, I think, from 2018. It's already there, out there, and is in the testing period, obviously, or trial period. Hopefully, if I can get someone available, I will put the interview about GDA 2020 and give you some information about the new datums coming up. But make sure you also go and search and understand what's the difference between the new datum and the previous datum, what has been improved, what hasn't, or because by the time you're going to be graduate, you're no longer using the old datum, from what I know. Okay, so we know what's positional uncertainty. Let's move on to survey uncertainty. What's the difference between survey uncertainty and positional uncertainty? They're all giving you uncertainty in the position of the point. Am I right? But one of them is giving you the uncertainty regarding the datum, relative to the datum, which I told you is going to be national datum stations. But if you have a local network, surveying network, then the uncertainty of the position of the points would be uncertainty relative to the local survey, which we call this survey uncertainty. Good, so it's relative to local survey. Example would be a control network that you can see. So you can see it's different from positional uncertainty. So basically in this way, or in this example, this is the survey uncertainty relates to the adjustment of the network, which is surrounded by few stations, you can see, where there is a minimal constraint on adjustment. SU becomes the definition for a station in the local network. So anyway, this is relative to the local survey. How about relative uncertainty? How about the relative uncertainty is basically uncertainty between two survey points within the control limits. And what it shows is basically shows the uncertainty of the distance and angle measurement. So how it can be used is really easy. When I'm saying angle, I'm talking about bearing, obviously. So RU is basically a valuable measure to assess systematics and gross errors. Let's have an example for you. If we assume the RU, or relative uncertainty between the stations, shows a distance uncertainty of say distance uncertainty between 2 points is roughly 11 millimeter. Say this is at 95% confident interval. Good. Over 240 meter. Good. So if the distance between them is 240 meter and the relative uncertainty or RU is 11 meter at 95 confidence interval, and then we assume we use the equipment with the accuracy of, say, 3 plus or minus, obviously 3 millimeter plus 2 ppm, part per million, good, which is the ADM accuracy. My question is, what would be the uncertainty for, like, what's the positional uncertainty or survey uncertainty in this case, and what is the relative uncertainty, which I already told you, relative uncertainty is 11 meter. Let's say if I want to measure 240 meters using this instrument, what would be the manufacturer specification? According to manufacturer specification, I should have 3 millimeter plus obviously 2 ppm times 240 meter, so it's roughly 3.6 millimeter plus or minus. So this is sigma, so it's at 68%. If I want to have at 95% confidence interval, it should be double up, so it's roughly 7.2 millimeter, so, or 2 sigma. Yep, so it gives you 95% confidence interval. So this is the accuracy we can achieve using that instrument. But you can see relative uncertainty is basically more than what we can achieve using the equipment. So it gives you the hint that errors may exist in the control survey, because relative uncertainty that we have is much more than what we can achieve with the equipment. So this is how it can be used to identify the gross error or basically systematic error in your measurement. So I'm talking about uncertainty, but I want to also tell you what's the difference between the precision and accuracy. You all know this diagram, so pretty sure you know, but just repeating. If I say this diagram shows the accurate and precise, so our true or roughly true value should be here in the middle, and all of our measurement is around that, so it's perfect, accurate and precise. But this example shows the accurate, so it's roughly around the true value, but it's not precise. You can see measurement is all over the place. This one is not even accurate and is not even precise, but this one is precise but not accurate. It shows the value but is not accurate. So let's give you an example. For example, if you forget to put the prism constant error into your instrument, what would happen? You're measuring, if you measure the distance 20 times, you're going to get the precise measurement. You're going to say, if I measure 20 times, every time I'm getting very close to what it should be within 1 mil. Yep, 51. So these measurements are precise. They're very close to each other, like this example. But are they accurate? No, because they're out by, I don't know, 32 millimeter, if that's the prism constant for your instrument, from the true value. So your measurement can be precise but not accurate. Or maybe another example, which before I move on, is, for example, if you have a broken clock, yep, it's not working, but at least twice per day it shows the correct time. But you might have an expensive clock which is dropping by a second, say every minute or whatever. So it doesn't show the true value in millions, in 100 years time or 200 years time, because it's never going to be accurate, or and this is not really worth it. So I hope I gave you indication what is precise and what is accurate. So some of the terminology in error analysis, like let's have a look at how we're going to evaluate the measurement uncertainty estimates. There are two types of estimation. First of all, you might do type A, which I call it. In type A, for example, you measure 100 distances under the controlled and measured condition and compute the standard deviation for that sample. And then it's going to be your uncertainty for that measurement. So you have the sample to test. Or type B would be, you don't want to do that. So you simply can use equipment specification and or previous experience that you have and weight your observation accordingly. So if I want to summarize, type A is the basic estimation of the measurement uncertainty based on a statistical analysis that you're going to do yourself, as I say, in the control condition. So if I wanted to measure the distance, 100 meters distance, hopefully, under control condition, say like 20 times, and then I can get the sigma for that sample size. It's going to be, can be used as uncertainty, or I can use simply manufacturer specification report that someone else has did for this equipment. The other terms, if you look at the study book, there are many of terms in the study book that you can go and scan through. Many of them you know some of the terms. There are only a couple of the new terms which I put it here just to explain to you. The other term which might be new for you is the coverage factor, or K. What is coverage factor is basically is a number which can be multiplied by your standard deviation to give you the different confidence level. For example, I told you sigma in the manufacturer is at 68 confidence level, 68%. What does it mean? It means that 34% of your observation might not get the accuracy is written in the manufacturer specification. But if you want to have better confidence interval, like say you want to measure the in 95% confidence interval, then you will multiply that sigma by 2. If the sigma, for example, is 3 millimeter plus or minus at 68% confidence interval, it becomes 2 plus or minus 6 millimeter at 95% confidence level. So we know what's the coverage factor. It can be, if you go to 99, it's even less. It's even more, it's 3 point something. But what is the other terms? Is circular confidence region. Circular confidence region is mostly used in GNSS analysis and is very popular nowadays in standards and specification. That's why I put it here, because you've heard about error ellipse, but not really about circular confidence, so it's pretty much new. So CCR is given later. Obviously, I'm talking about that in more detail, but is linked to other special data set from the need to match GNSS definition of uncertainty and also GIS general specification for describing uncertainty. So as I said, I will cover it later when we are talking about error ellipse. So what's the next one is uncertainty budget. So you will see uncertainty budget in module 1 and 2. So it's good, you should have the good understanding what's uncertainty budget. As is written, is a statement of measurement uncertainty, the component and combination of the measurement uncertainty. What does it really mean? It's basically a way of ensuring all uncertainties are accounted for. So we make sure that, for example, if I want to give you a specific example, I would say radiation, for example, would include uncertainty in bearing, distance, height of instrument, height of target, setup, atmospheric, and so on. So when you're measuring something, there are few combinations of uncertainty. It's not only uncertainty of that measurement. Like when I'm setting up my instrument, I might have some uncertainty related to my setup or height of instrument, or measuring the height of instrument, measuring the height of circuit. All those going to affect the final results. So the combination of them is going to be uncertainty budget. So I put 3 examples here, and in the study book obviously you can see them. And then if in the exam you're running out the time, you don't want to listen to the whole lecture, you obviously can go. I put some voice or talking point that you can play and listen to them. So I'm talking about some of the diagrams that I feel might be complicated for you. But let's say if I have point A, yep, just as a normal surveying, and I'm measuring to the point A, L is my slope distance. I have a delta H, which is a height difference between where I set up my instrument and point A, and I have a dA as a horizontal distance. I have a theta, which is, in this case, as you can see, I put horizontal and this vertical. So it's going to be my zenith angle. So simply, if in surveying, we're just measuring the bearing, zenith angle, and L. So this can be calculated from this observation, yep, using these 2 formula, which is easily can be done using trigonometric rules. So let's move on. Let's say we introduce the error in measuring our zenith angle, which is that small a. So if I'm measuring, for example, my zenith angle within 3 seconds off, good, is less than what it should be, then you can see how it's affecting the delta H and horizontal distance. So my horizontal distance is going to be less than what it is, and the delta H is obviously going to be more than what it is. So it's error in one measurement, which in this case, you're going to see how error in angle can affect the linear measurement. So its angle is not linear, but it's going to affect our measurement of the height and horizontal distance. So if you have an error in zenith angle, you can't really simply change the angle only measurements and say, oh, that's it, I fixed the error. No, it's not like that. It's already affected other measurements. So we have to really make sure that we understand how it's going to impact our measurement, how we're going to rectify that error. Same story if you have more error, like I'll say previous example, I measured the zenith angle less than what it is, so I have minus e. It can be plus e or small e, which is the error in this case. Again, you can see how the position of the point can change, which is also affecting the height of the points as well as the horizontal distance. So it can be more or less. Good. So this case, if we have a plus 1, for example, the delta H would be less than what it should be, and horizontal distance is basically more than what it should be. So this is an example, basically, how the error in height due to zenith angle going to affect the basically horizontal and vertical, horizontal and height differences, basically, which can easily calculated, obviously, using the trigonometric formula, as you can see from the right angle triangles we have here. Let's move on. That was the error in zenith angle, but how about if we have the error in distance? Does it affect our angles? The answer is no. So if you have any linear error, like in the linear measurement like distance, it doesn't affect the angle, but if you have any error in angle, it does affect the either horizontal distance or height differences, depends on bearing or obviously zenith angle, or it can affect both. So if I have error, if LA is my slope distance and I have plus and minus small l error in measuring the distance for point A, then it does affect again the height difference as well as the horizontal distance for that point. This is another example, but in this example, now we have the error in bearing. Yeah. So if we have an error in measuring the bearing, obviously it doesn't affect the slope distance, but it does affect the basically the easting and northing for this point. Can you see? The point has changed. So it doesn't affect the height, it doesn't affect the horizontal distance, but it does relocate the point, which is going to have different delta easting and northing than what it should have. And also yeah, it shows is basically the picture is self-explanatory. Let's move on. So we've talked about the errors and uncertainties. Now I want to divide the errors into different types, systematic and random error. We all know what systematic and random errors. I'm just going to give you a little bit of review and then more talk about the surveying example of them. So a systematic error is basically if you have the error that is basically related to you forgot to insert the atmospheric correction, or you forgot to insert the prism constant. These are the systematic error. What is random error is basically the accuracy or standard deviation that you get from manufacturer, for example, that you have plus or minus 3 seconds errors you could have in measuring the the horizontal vertical angles. It can be the error associated on verticality of the pole. These are the random error that can happen. But no matter whether they're systematic and random errors, they can be categorized in 3 types. Either they're constant error, errors that have same magnitude no matter and sign, no matter what's your measurement quantity. Like if I have prism constant error not inserted into the instrument, no matter I'm measuring 10 meter distance or 200 meter distance, is going to be the same effect. Good. So if I want to correct them, I have to, for example, plus or minus 35 millimeter, or if it's inserted in a wrong sign, I probably should double up the errors. But some of the errors are proportional errors. What proportional errors? It means that it's proportional to the quantity of the measurement. For example, if you haven't corrected your distance for curvature and refraction error, as you measure, it doesn't show itself, for example, for shorter distance, but as you measure the long distance, for example, over 200 meters, it's going to show itself, and it's going to affect your measurement more. So it's proportional to the measured distance in this example. So other examples would be atmospheric scale factor, zone scale factor, as I said, curvature and refraction. So the other or last one is periodic errors. What's periodic errors? The error can occur from time to time, usually following the harmonic pattern. What is harmonic? What's the example? I made a mistake here. Curvature was for proportional, and refraction can be periodic because atmospheric refraction is changing from time to time. If you measure that at the start of your survey, and you're measuring at the end, so it might be different. So these are the considerations we should have when we are doing the survey. So it can be constant, so it doesn't matter what you measure, it's going to be constant. Proportional, so it's proportional to the quantity of measurement. It can be periodic, changing within time. It's like temperature, for example. So, systematic error, as I said, they're classified as natural, instrumental, personal, and computational. So it can be from any of those sources. It can be personal issues, or I forgot to put in it. It can be instrumental issues, so it can be any sources. How we can minimize them or make sure that we don't have these things? First of all, calibration. Make sure that whenever you're using your instrument is calibrated, and make sure that the condition is met. Observation condition, like you have the, you've inserted all the atmospheric correction, and make sure that you follow the procedure that is required again. So if you do that, you basically can make sure that you minimize the mistake in terms of systematic error. If you, for example, if you go out there, every time you make sure that you check, okay, I set up my instrument and make sure I put on the prism constant correctly, I've put on the temperature and pressure correctly, everything is alright, I make sure that I apply curvature and refraction, or if I don't want to apply and I want to apply in software. If you remember, we had in the automated surveying, again, an example that I've asked a student to compare the calculation with the software. And the end result would be, if you don't know what software does apply or your instrument is going to apply, you're probably going to double up your error. Like if you apply curvature and refraction in the instrument and in the software, you're in trouble. Or if you forgot to insert in either of them or both of them, again you're in trouble. So you make sure that you understand what your software or instrument settings is and how you're going to make sure that you follow the correct procedure to get the correct measurement. So I've put the list of the systematic error. You can find it in the module 1. So I just give you a couple of examples to make sense of systematic versus random error. Systematic error, as I mentioned over and over, is going to be prism constants. If you put it wrong in a wrong sign, it's going to be double. Just make sure that, like if it's my prism constant is minus 35 millimeter. If I write I'm putting minus 5, I put plus 35 millimeter. Is basically the error you're going to have is 70 millimeter, because your error is going to be twice as much as it should be. So how you're going to detect it is really hard to detect, especially if it's a closed traverse. Basically, you have to make sure that you do that, and every time you set up, you, as I said, check your measurement. How you can remove it, obviously make sure you do the EDM calibration or calibration instrument. The simple 3-peg test can give you the hints what's the prism constant for your instrument, whether it's, if it's not written, obviously it's always written, you can read it, but if you are not quite sure, you can do the simple 3-peg test to find out what's the prism constant. So another example is non-verticality of your prism pole. If bubble, for example, if it's not vertical and your bubble has an error in the pole position, first of all, you always make sure that the bubble is alright, it's working fine, or it's not broken, obviously. If it's broken, try to adjust your bubble and make sure that you hold the prism as vertical as you can. The last one is the collimation and other instruments. Nowadays, all the robotic total station has a procedure that you can check the collimation, horizontal and vertical collimation, and teeth errors, and you can adjust it in the instrument. There's also a simple field test that you can do and then find out. We know all about those tests again to fix the collimation errors and make sure that our instrument is calibrated. These are the systematic errors, but how about random errors? Random errors is basically has the Gaussian distribution or normal distribution. As I said, the Gaussian distribution or normal distribution, as you can see in the left hand side. On the right hand side, I put the picture of the Gauss. Gauss used to be a mathematician and a surveyor, if you don't know, and scientists who did a great job in basically in many fields, not even surveying, of Gaussian distribution or normal distribution is basically used in wide range of fields, but he was very famous in geodesy, geophysics, astronomy, electrostatics, and many other fields. He's also formulated the coefficient for refraction, which is still used today. So I just put the bank note which showing his picture, so I found it good to know him. Yep. So surveyors can determine their own standard deviation if they want through the sampling a large number of observations. So as I said, if you have a distance and if you measure it over and over for say 50 times and then get the standard deviation of that sample, you can use that one. but it's always difficult to do that. If just imagine we want to do that for each observation, it's just impossible. What we do, we're just using manufacturer specification for random errors. So, just a hint. When you're using manufacturer specification, as you can see on the right-hand side, I put the example of manufacturer standard deviation and how they measure that. Obviously, it shows that, for example, if for 500 meters, what's the standard deviation of the distance, for example, so, and if it's larger than what's going to be the standard deviation. And but just remember, as I mentioned before, and we're going to measure it over and over. I know you're going to be bored, but it's very important to know all those standard deviation or sigma are at 68% confidence interval or confidence level. So if you want to achieve 95% confidence interval, what do? We multiply them on 1.96 or 2. So these are the sigma. If I want that, I have to multiply that. So we have the random errors for each of our measurements. It can be a distance, angle, instrument, tilt, and so on. So it can be found in manufacturer specification. How you can find it? Easily Google it. Good. You can Google anything and find the instrument manufacturer specification if you don't have it with you or your company doesn't have it. It's easy to find. What are the typical random errors? So random error can be recording or reading observations, so I can book it wrongly. It might be a sighting error. How you can mitigate it? Make sure that you, with this robotic total session, ATR, automatic target recognition, basically is minimized quite significantly compared to the, I don't know, 10, 20 years time. But we should also be able to assess the pointing error from instrument specification and our own experiences. Obviously, distance is important, so basically magnitude is going to change. It's proportional to the distance, what we say. So it can be an offset measurement if you're measuring the, again, distance using the tab. It can be height of instrument, height of target, and so on. You can find a whole list of that and their description, mitigation, magnitude in the module 1. You can go and scan through, make sure you understand them. I think these are very important to know. So here's the thing. Sometimes you will find some errors that you're not quite sure whether they're systematic or random error. So often the random error forms part of the systematic error or correction. Manufacturers of total station often present a formula for, say, atmospheric scale factor in part per million, as we know. Most manuals state that the correction will be less than 1 ppm under the following conditions. What does it mean? It means that if the random errors of the atmospheric condition are met, then the systematic error in a scale ppm is less than 1 ppm in this case. This is the example where a systematic error is counted in the uncertainty budget as a random error. So it means that it's very small. Yep. If your systematic is very small, what they say, and your condition is met, the atmospheric condition, it can be counted as a random error. But don't be confused. Just you might see this type of thing, but it's not very common, obviously. The other thing I want to say you, we do have the random errors. Yeah, we have the in the manufacturer specification, for example, you might see the accuracy of measuring the angle, for example, like vertical in this example, I don't know, say I have a 10-second accuracy for measuring the vertical angle. But if I'm measuring that, horizontal angle, but if I'm measuring that 25 times, is that still 10 seconds or not? First of all, if you're repeating the observation, you're going to have more precise. Do you remember we talked about precision and accuracy? So you're going to have better or precise measurement. But what's going to be the mean of the standard deviation or the accuracy? If I'm measuring that angle of bearing for 1 time, it's going to be 3 seconds. But if I'm measuring that angles like 25 times, the standard of deviation of the mean would be 10 seconds divided by 25, sorry, 25. And then it's going to be 20 seconds if I'm measuring 25 times, sorry, my bad handwriting. So it's going to be 25 squared, root squared, so it's going to be 5 and then 2 seconds. So I'm going to have better or more precise measurement. So the hint is, if you have the instrument which its accuracy is not good enough for your purpose, you can always think of repeating the measurement to get the better accuracy for your final results. So for example, if I have the distance that I need, for example, our accuracy of my distance measurement is 10 mil, yep, plus or minus 10 mil, but I want to achieve 5 mil accuracy, and I can measure it 2 ways. Good, like from A to B, B to A. So in this way I can reduce my accuracy by 5 mils, for example. So these are the hints you can do. But if that's the case, you might say, okay, I'm also doing that for 100 times or 30 times to get most precise I can do. But why I put this figure here? To show you, yes, the accuracy is significantly or increasing as you increase the number of observations. But you can see from 11 or 15, 11, it's not hugely changing. So I would say if you want to have the best bet, 5 times is the best you can do. After that, like see from 5 it dropped to 2, but after that if you're measuring 30 times, it's only improving by 1 mil, which is not huge and it's not really critical. So this is a thing that you can do in order to improve the precision and accuracy for your observation. In the next few slides, we've learned about the error, we've learned about systematic and random errors, obviously, and we've learned that if we increase the number of measurements, we're probably going to have better or more precise results at the end. But in the next few slides, I want to talk about propagation of the systematic and random errors. Let's start from systematic errors. If you have a linear function as a g, like if there's a linear relationship between our measurements, the final error or the basic combination of that error, which we call it error propagation, at the end is going to be just simply adding up like EA, EB to EN. Like if each of them are related to one of those observations and there's a linear relationship between them, if I add them up, EG is going to be my propagation and final errors that I'm going to have, considering all of those errors. But is that the case in real world? No. Most of the time you don't see linear, and most of the relationships are non-linear. So then you would say, what would be the error propagation if I have a non-linear relationship? So the answer is, you can use the derivative formula. If I have the function f, which is non-linear, as you can see, and I have the variable a, b, c to n, with the systematic error associated with each of them, say EA, EB to EN, the impacts of each systematic error is the propagation of the partial derivative of the function with respect to each of those variables multiplied by systematic error. What does it mean? It means that if I have a f, good, which is nonlinear as I said, and is basically function of a, b to n, and each of these observations has accuracy related EA to EB to EN. my error propagation can be written as partial derivative of f with respect to a multiplied to accuracy of a, partial derivative of b, f with respect to b, obviously, then b, and then so on to n. Here's the hint. If you always use the nonlinear formula, even if they have the linear relation, it's going to give you the same answer. I can show you the example, so you're going to realize why I'm saying that. But if I want to give you the very clear example, say I have a L, which is distance, which is basically, if I'm adding L1 plus L2, is going to be the total length of that distance. Good. And they have a linear formula. But if I want to use this formula and get the error propagation for AL, I can say is going to be of f, in this case, is L1 plus L2. So what's going to be, my function is basically L1 plus L2. Yeah, do you agree? And then in respect to L1 plus, to multiply, so EL1 plus partial derivative of f to L2 times EL2. So partial derivative with respect to L is going to be 1. Sorry. Partial derivative in respect to L2 is going to be 1 because this is the linear. So I can simply say EL is EL1 plus EL2. If I'm coming back one slide, you can see, because the relationship was linear, but easily if you add them up, the accuracy of two measurements, it's going to give you the final systematic error propagation or systematic error. So what I want to say, yes, we know we have a linear and non-linear, but what we call it linearization is across, for example, in this example, across the range of 0 to 180 degrees of the sine function. I just draw the sine function part, you know, we have sine function like this, yeah? I just draw this bit here. So it's from 0 to 180. You can see that the sine function is clearly nonlinear, but as a smaller increment, if I'm just looking at 0 to 1, so this bit here probably, and enlarge that. If I'm only considering sine of zenith angle from 0 to 1 degree rather than 0 to 180 degree, you can see it's going to be a linear function. So this is the basically theory behind many of, if I want to say, is the theory behind the Taylor series, if you've heard the name, which is that derivative of a function over a small increment approaches a linear displacement. So if you look at the smaller piece of that function, might be linear. Good. It's always like that, to be honest. So that's why you can assume that systematic or linear. In this example, if we look at the 0 to 1 degree only, smaller increments, basically a small increment, basically. So let's have a look at another example of nonlinear. So in this example, I want to look at the simple systematic error propagation for the horizontal distance. Reduction of the slope distance L to basically dA, which is the horizontal distance. We all know from surveying A, if you have a zenith angle and slope distance, we can simply calculate the horizontal distance, which would be L, so dA is L times sine of theta. Good. If I replace L, which is in this case 250, and I replace theta, which is 75 here, and L is 250, I can get dA as 241.481 meter. Good. But let's have a look. Say if we have, this is in the perfect world if we measured everything without any error. But if we have an error of plus 30 millimeter in the slope distance and plus 30 seconds in zenith angle, how are they going to affect the final accuracy of the horizontal distance measurement? So, given the systematic error, in the first scenario, we're just including the error in the distance first, yeah, assuming that the theta is alright. So if I say I have the error in my distance, which is like 250 plus 30 millimeter times sine of theta, good, and then I subtracted the true value case, so I'm gonna have 29 millimeter error in the final results if I only have an error in the distance. In the second scenario, I would say, okay, let's just ignore the distance and say if we only have 30 seconds error in our measurement of zenith angle, how is going to affect our final accuracy? Yeah. In this case, I will leave the L as it is, and then I say sine of theta in this case would be 75 degree 0 minute and 30 seconds. Yep. And then I would say, so how it's gonna affect, so is I have the true value here, I can compute this value from here, and then I can say it's 9 millimeter, it's gonna affect by 9 millimeter. So what is it? Is basically, but what's going to be cumulative, what's the end result? Yeah, I can ignore one and another and get the value, but what's going to be combination of those two errors? If I have both errors, if I have error in distance and error in measuring the zenith angle, how is going to be my end result? Systematic error, here's the rule. Systematic errors are cumulative, so they can be added, yeah. So I can simply add these two, and I can say if I have error in those two, it's going to affect my measurement by 38 millimeters. My final result is going to be out by 38 millimeters. This is the example we just put and analyzed. But if you just want to use the formula we had previously, do you remember I had the error propagation for systematic error? If I say using the nonlinear error propagation, if you kind of remember, we had d is our function here, so it's L sine of theta. Good. So if I use this derivative, partial derivative regarding to L, it's going to be sine of theta times to E of L, which is sigma L, and plus to partial derivative of d toward theta, which is L times cosine of theta, multiplying by accuracy of zenith angle measurement, or errors in zenith angle measurement, then I can get the result. The hint is, remember, you always, whenever you put the angles accuracy, in this example was 30 seconds, yep, you have to convert it to the radian. That's why you can, if it has been converted to radian and put into the equation. You can see I can get the same result. So no matter which method you are going, you're going to end up having the same answer at the end. So hopefully this gives you enough insight about the error propagation and basically for the systematic error. There are more examples in the study book that you can go and have a look and try to see whether you understand the concept good or not. But let's move on for now. But my question is it easy to identify the systematic errors? Not really. I will give you an example. Just let's have a look at the closed traverse. if we have a closed traverse running from A to B, C, D, and coming back to A, obviously, we say our misclosure, linear misclosure, obviously for delta easting, delta nosing, is 5 mil and 7 mil respectively. And the traverse misclose ratio is quite good. It's 1 over 100,000. And I would say, yeah, that's perfect. This is what I want. It meets the requirement. And I'm quite happy. Let's say we add 1 meter error, systematic error, to each of those traverse legs. Let's say, right now I'm measuring, I don't know, 1 meter, I measure 2 meter. So I'm adding 1 meter to each of those legs, yeah, those 4, which becomes the one next below that. Again, if you calculate misclosure, you're still going to have 7 mil and 5 mil, and then misclosure for nosing and easting, and then you're going to have traverse misclose ratio of 1 over 100,000. So it's really difficult to identify those. So you can easily have the systematic error and never find out or identify that. So it can go undetected, especially in the closed traverse. It's really hard to identify. But if it's not closed, if it's starting from, for example, in this example, starting from O1 going to O2, it's a little bit easier to identify those systematic error in the open traverse, not open, still it's closed, but it's from 2 known points, not closing on itself. So in this example, for example, you can see our misclosure for the easting and nosing, easting and nosing is 16 millimeter and 96 millimeter respectively. So obviously it's not good enough. If you get the misclose ratio, it's going to be 1 over 10,000, which is not even near what is acceptable for contrast survey. What should we do? How we can identify where is our error? How are we going to rectify that? How are we going to correct our observation, or shall we redo the whole thing? In this example, which is very important, and we have the similar question in assignment 1, so it's good to understand that. So I started from O1 to O2. So if you look at the traverse, it's going south-north basically. So it's going northward direction. And so I'm going from O1 to O8. And then I have A to B, again I'm going up. I have a B to C, C to D, and D to A. The hint is our easting misclosure is not too bad, but our nosing is too much, like 96 is way above what it should be. If you look at the traverse we have here, you can see B, C, and D to O2. They're pretty much parallel. From what you can see is B to C is 90 degrees and 270. They're parallel to each other in east, west, and west is direction, and they cancel. If they have any error, they cancel each other error because they're in 2 different directions. Yep, and they're parallel. So if I exclude those legs, it's going to be 3 legs only. 1, 2, 3 in, as I said, northward direction. What you can do, you can divide 0.096 divided by 3 is going to be 0.032 meter, which is roughly 32 millimeter. If you know your prism constant is 33, say, plus 33 millimeter, you can say or guess that, oh, I might put, I must have forgotten to put my prism constant, so that's why I have this error. So what you can do, you can come back, you can adjust your distance, yep, you can add or subtract, depends on the sign of the prism constant, adjust your distance, evaluate your results again. So I'm sorry, I forgot to put it here. You can see the answers in the study book. So you can see I've adjusted the distance, and then I've adjusted the delta East English signosing accordingly. And then once you're gonna go back, you can see the final result. You're gonna have 1 over 100,000 basically misclose ratio, which is acceptable in this time. So it's basically what you need to do. You have to find out which direction your traverse is going, whether you have any parallel legs that they cancel each other's error, and then you find out which direction you have more error, like 96 degrees in this case, and then divide it by number of legs you have, and then you can guesstimate what was your error source of the error you had, or systematic errors. Another example, just imagine you have the this nice diagram that I've drawn, which has a very good story, which I'm going to tell you. Just imagine 2 surveyors. One was actually actual surveyor, and one of the basically surveying A. 2 surveyors do each side of line windowing roughly 26 kilometer traverse orientated north-south. The misclose is around 0.6 meter. Obviously not good. Survey A experienced a touch arrogance, says he has checked everything and all his calcs and is sure his works is okay. Yeah. So this is survey A, and this is survey B. They did both the same traverse, but they're not having a different, like this is 26K roughly, each did 13K, but they're pretty sure that they all did good. Survey B is a young USQ graduate. Yeah, it's you probably going out there as a graduate. Also checked, in this case, I try to be have 2 genders, like he and she. So her works or her calcs and finds nothing. Then noticing that there was 10 legs on each side. So if I'm counting the legs, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 sides each leg. If I divide, the misclose they had is 0.6 meter. So if I divide 0.6 meter by 10, what would be the result? Is around 60 millimeter per leg. I'm right, because the traverse is going northward direction, so south north. So 60 millimeter per leg, and if we know the EDM index or prism constant index is 30 plus 30 millimeter, what would be your guess? Being a well-educated from the finest university, yeah, USQ, she does a 3-peg test, and then she found out, oh, hang on, I think we've entered the prism constant with wrong signs. Right, and I put it plus 30 millimeter. They put minus 33 millimeter. Sorry. So then that's why they have double up of that number. So always assume you're wrong. This is the conclusion for this story. So don't be overconfident about what you're doing. Always check your work. Always make sure that you did everything right. So if you put the prism constant in wrong sign, you might end up having double up of the error that you double up your error basically. So let's move on to propagation of the random errors. Random errors follow the laws of normal distribution, as we said, Gaussian distribution, and they propagate with variance. Variance is the square root of the sigma. The variance of results, a linear function, is the sum simply. If we have a linear function, again, do you remember the example we have from systematic error looked like that? This is for random error, so it's a square root of, or I would say, variance is basically a square root of sigma. So if someone add them up, it's going to be the error propagation for random error. This is for linear function, but how about the nonlinear function? It's pretty much the same, but it's squared. Again, if you remember the systematic error, it was the square if only the partial derivative formula multiplying the systematic error for each of those variable. But in this one, we have the square of each of them. So it's partial derivative multiplying by sigma of that with respect to a, multiply the sigma a, and so on. So this is when you don't have any relationship or your observation are independent, there is no covariance between your observation. But we all know from this square adjustment comes B, obviously. You might have a covariance between the your observation. For in this case, then you might have variation of the formula we had before. So you will have basically covariance between the observation added to here. Do you remember matrix of variance covariance from comes B? Hopefully you do. But in this course, I'm not looking at this bit here. So we just imagine they're all independent. For error analysis is mostly they're independent from each other. But if you are doing this square adjustment, for example, it's very important to consider the covariance between the variance covariance matrix. But for simplification of this, we don't consider covariance in this module. Let's look at the example of propagation of the random errors. We did have an example for propagation of systematic error. Just have a look at the random error. If I want to measure off the height of basically inaccessible tower on the top of the building, what would be, if I do have a total station, my option is I set up my total station, I measure to the top of the building, I measure to the top of the tower, and then if I subtract them from each other, those heights, it's going to give me the height of tower. And simply, if you measure the horizontal distance and basically vertical angles, you can simply calculate the height for the buildings, and then overall, and then you can come up with the, subtract them from each other, get the height of tower. So if I'm doing that, if I'm taking the instrument out, measure those, and say I've measured these numbers here, and from this instrument specification, I know the random error for each of my measurements, like distance and like alpha and beta, which are both vertical angles, so it's going to be the same, plus or minus 10 seconds, plus or minus 10 mu for distance. So let's go back and say what the true value would be. So if I just put these numbers here in the formula, I can get the H and HB, which is the height of building. So, and height of target, height of tower is height minus height of building, the total one minus this. So, which is the tangent of beta minus the tan of alpha. Okay, I'm just double checking. Yes, I'm right. And then from the formula we had before, which is the squared of those sigma partial derivative formula we had, so I can measure the height of towers. So basically partial derivative of f, which is this function here, in respect to d is going to be tan of beta multiplying sigma d squared plus tan of alpha multiplying sigma d squared. Yeah, this is this bit here. Yep. And then I have partial derivative of f in respect to alpha is going to be, sorry, this is in respect to beta, this is in respect to alpha. I put it in the wrong order. So if I just put all the numbers I had into this formula, I ended up having square root of the height of tower is 3.96 times basically 40 millimeter, which if this is a square root, yeah, but the sigma would be, sorry, of this number here, which is plus or minus 20 millimeter. And remember, sigma is 68 confidence level, 68% confidence level. So I can measure the height of tower and I can easily find out from the trigonometric rule with accuracy of 20 millimeter plus or minus. If I have a look at the partial of those equations, you can see major contribution is from vertical angle and slope, sorry, in this case is the horizontal distance or distance. But what it shows you, basically, it shows you if you want, so you can see I put these numbers here. So if I'm changing the accuracy for the angle or distance measurement, it's going to affect the accuracy of measuring the height of towers or end result. So remember, I had 20 millimeter plus or minus 20 millimeter at 68% confidence level. But if you want to have 95% confidence level, you might want to double up the number. As you see, 2 sigma is 95% confidence interval. So if I times 20 millimeter by 2, it's going to be 40 millimeter plus or minus, obviously, at 95% confidence level. So if our job specification require the height of tower to be measured to plus or minus 25 millimeter at 95% confidence interval, then the measurement we had is not enough to meet the standard. What we can do, there are a few things we can do. The first scenario, I can read my vertical angles 4 times, 4 sets of vertical angles. So do you remember this? I had the sigma of mean, gonna be sigma number of observations. So if I'm measuring 4 times, it's going to be 10 divided by square root of 4, which is plus or minus 5 seconds. So it's going to reduce it's going to bring the more precise angle measurement. And if I, for example, if I want to increase the distance measurement, which was plus or minus 10 millimeter, I believe, I can measure the distance in 2 ways and basically reduce it by plus or minus 5 mil. So if I put those numbers, chunk these 2 numbers rather than the accuracy I had before, I'm going to achieve the sigma plus or minus 10 mil, which is at 95% confidence interval, is going to be 20 millimeter. So if you want to achieve the 25 millimeter accuracy at 95% confidence interval to measuring the height of tower, you have to measure the angle 4 sets and distance in 2 ways, basically. This is how you can analyze your result, and you can see it's very easy and it's very simple if you think. So I put the video in the module 1. I will show you at the end of this lecture where you can find it, obviously, but you can do lots of this, and this is just one example. But just imagine you want to do for many observations. It's really hard if you have too many variables and you want to test different, like zenith angle, different bearings, different numbers. So what you can do, you can simply do all those analyses in Excel. You can try different number of the, for example, test different number of the distances, different number of the zenith angles, yep, different numbers of bearings, and then you can come up with delta AC nursing H, and then different basically analyze the accuracy. If the distance getting bigger, how it's going to affect. If I'm measuring the zenith angle in different angles, how it affect the final accuracy of AC nursing and height, you know. So you do all those analysis if you have the instrument specification from your manual manufacturer specification. Sorry, I've shown that here, so you can go and have a look how you can create such a thing. But you can see if we measure the longer distance, obviously most of our arrows are proportional, so it's gonna getting bigger. Some of them doesn't change hugely, but some of them yes, like height. You can see it is affecting the height, but doesn't really bearings is affecting. So it's kind of what we showed in the diagrams in figure 1.2 and 1.3, obviously how they affect each other accuracy, but you can also try it yourself. So this is another example. In this example, we, rather than just having the random arrows, which is from manufacturer's specification, we try to bring others arrow like pointing accuracy, or like you can see height of instrument, height of target arrow. Like, do you remember we had the random arrows associated to that? We can also insert the verticality or prism index measurement. So you can bring many more arrows and look at the propagation and how they can affect the final accuracy if you like, and create Excel sheet. Again, you can go to the module 1 where I put the video embedded in the PDF, and you can play them and see how you can do that. So this example is a little bit different from what I show you. So far I show you how you can measure and how is, if you have any errors in, for example, in the previous figure we had figure 1.2, I show you how if you have the error in zenith angle, it's going to affect the accuracy, it's going to affect your horizontal distance and height accuracy. But that was for measurement. But if you want to set out rather than measuring, then we probably don't have any, because when you're setting out, the horizontal distance is fixed, yeah, we know that. If you want to set out, then the more likely you will get, look at this example and this example. So the points are in line, yep, and then you have the, as you can see, the arrows in the zenith angle is going to affect our delta H. You can get it through trigonometric formula, and as well as obviously the slope distance. You're going to have different ones, but the horizontal distance is fixed in this example. So I will stop this video here, and then I will record the second lecture 1 because it's getting too long. So I separated in 2. Hopefully you're gonna listen to that. Thank you.